Yeah, affinity biosensor. So affinity biosensor depend on irreversible binding. Yeah, this is the difference with catalytic biosensor, like the one that uses enzyme or whole microorganism. In affinity biosensor, the binding is irreversible after binds to the target molecule. Then very difficult. The dissociation constant is very small. So affinity biosensor, they are like the one that uses antibodies, nucleic acid, or receptor. The primary sensing event does not result from catalysis like enzyme or microorganism. Okay, but on this binding of the affinity biomolecule with the target molecule. And so that is why usually it is not easy to detect any electron exchange, because if you want to detect current, usually there has to be electron exchange. Some electrons are being captured, some electrons are being given to the reaction system. And in affinity, no reaction, no electron change. So how can we detect this binding event between the biomolecule and the target molecule? And we have to detect other physical changes, such as heat. For example, some heat are being dissipated or being absorbed. Then we can use thermistor, very high sensitive thermistor, of course. Or more sensitively, we can use mass change. When there is a binding and it forms a complex, then mass will change. So we can use various mass detecting physical transducer that we have learned so far. Yeah, QCM, quartz crystal microbalance, surface acoustic wave, surface plasmon resonance using optical sensor. So let's learn now from the first part, yeah, using antibody and antigen, so which is called as antibody or antigen biosensor, or more generally as known as immunosensors. The immunosensors transduce the antigen antibody interaction into physical signal. Okay, and this usually is in the form of mass change. So antibodies are serum proteins. I think we'll go a bit quickly on this because most of this, I believe, you have learned in biochemistry. So antibodies, serum proteins produced by B lymphocyte and plasma cell. Yeah, it consists of four polypeptide subunits. An antibody consists of four polypeptide subunits comprising of two heavy chains and or H chains and two light chains, L chains. The carbohydrate residues in antibodies are covalently bonded to the C-terminal half Fc. The key portion of the antibody molecules that contain the antigen binding sites are termed FAB fragment, which contain an entire light chain and a segment of the heavy chain. Yeah. And comprises in this. So the antigen will interact with antibody to one of its antigenic determinant. This is like this. So we have the Fc subunit. This is the one, Fc is the one that is bonded, covalent bonded to the C-terminal half, yeah, the carbohydrate residues. And then it binds to FAB. This is the one that binding to the antigen that contains one heavy chain and one light chain, H and Pl. Okay. So if we want to prepare to have many binding sites, then what we can do is the covalently bind the Fc subunit to the substrate, yeah, surface, to the subsurface of the physical transducer. Yeah, but as I mentioned, this will require specific chemistry, mean more time, tedious, as well as more cost. So if you look one of my paper in 2014, we developed also biosensor using antibody, yeah, for beta-gonadotropin, but it is using cotton fabrics. And we don't use any specific chemistry, we just physically adsorb this antibody into the pore structure of the fabric. So it could be thought of as a matrix entrapment, basically. Yeah. The drawback, of course, then the antibody attached to the fabric will have different orientation. So sometimes it is this Fc, sometimes it is this binding site. And it will have more random orientation. Okay, so yeah, this is, as I mentioned earlier, this is a very important step, is the immobilization to detect, to immobilize antibodies antigen on the sensor surface to detect the corresponding antigen or antibody. Yeah, common methods include using self-assembled monolayer, using biotin avidin system, self-assembled monolayer, or glutaraldehyde linking method using protein A, and other indirect fixation methods. Okay. These are different methods of immobilization of immunosensor. Yeah, what is biotin avidin? Please later Google it, yeah, if you have time. So I will just mention here shortly. Biotin avidin, we have a protein called as avidin or streptoavidin. It has usually 4 binding sites. I use this during my master degree study, like this. And then the biotin is one avidin like this. This is avidin there, combined to 4 like this, to 4 biotin. This is biotin. This is the biotin. This is the biotin. And the red one that has 4 binding site is called the avidin. Okay. So yeah, this is also commonly used when, if you can, for example, modify the antibody, the Fc part of the antibody with biotin, yeah, like with the biotin using glutaraldehyde. Then basically, then you combine 4 of this antibody to using 1 avidin, or you combine this the other 2. You do S. You modify with S sulfur, yeah, sulfur functional group, so that it can bind the gold with self-assembled monolayer to gold surface. Then the other 2 you can put to bind antibody like this. So this is using biotin avidin immobilization system. Otherwise, immediately at the antibody, the FAC part, yeah, of the antibody, you modify it using peptide that has sulfur functional group. So in this case, then you may end up with, if you are using gold gold surface. Yeah, that's why if you read paper in biosensor, gold is very often used as the surface of the physical transducer. Then you can have self-assembled monolayer of the antibody like this, because the S can have interaction with gold, yeah, through, I don't know, usually it's not covalent also. Basically, it's not covalent binding, but there's a kind of electrostatic or some van der Waals interaction between sulfur and gold. You can have like this. So you see here the difference. If you use direct S modification to the FAC part of the antibody, then you don't have space between your antibody and the physical transducer. Okay, but if you use biotin avidin, you have this space between them. So how will they differ then? Of course, then in this case, the antibody cannot move around too much. Okay, so the interaction is also limited with the antigen. Yeah, if there's antigen flowing here, it has to be really in the vicinity of the surface such that it can bind to the antibody. On the other hand, if we have like this, a dangling antibody, that antibody that can still dancing around within some surface, some distance from the surface of the physical transducer, then it may be able to interact more freely, simulating a free antibody in a three-dimensional liquid solution. Yeah. But still with the advantage of surface interaction with the physical transducer. So this is when you develop a biosensor, you need to think carefully. What parameter you want to increase? You want to increase the sensitivity, selectivity, time response, or you want to minimize the cost? If you want to minimize the cost, which you can read in my paper in 2014, yeah, antibody, we use cotton fabric, yeah, like this, pore structure of cotton fabric, and directly we use physical immobilization of the antibody. So what does it mean with physical immobilization? So the antibody will be oriented randomly inside the pore structure of the fabric. Okay, so this is usually lower cost. Please Google Scholar. This one is my, I think, 2014 in Analytical Methods journal. My paper, quite long time ago. Yeah, very difficult now to produce such paper. Okay. Then, so this is the immunosensor made from antibody and antigen. And sometimes you don't want to detect the antigen, but instead you want to detect the antibody. In that case, you use then the antigen as the biorecognition element. For example, in nowadays, people want to measure their antibody response towards COVID-19, towards SARS-CoV-2 virus, whether they have already immune system. They already have this biosensor. I think if you go to Prodia, also they can provide this service, yeah, to detect. You take your blood sample and detect whether you already have some immunity towards SARS-CoV-2 virus. It means you want to detect the IgG and IgM related to the SARS-CoV-2. And the biosensor they use should contain then the whole virus particle, or otherwise only the spike protein of the SARS-CoV-2 virus. Okay, since time is up, we will continue tomorrow related to this affinity biosensor. Okay, the page is still long, actually, to go. I think we will complete by tomorrow to whatever page we can finish.